All right, great. Got it. All right. Thanks, Jim. Yeah, thanks for having me. I would much rather be there than in my garage right now before heading to court. But yeah, I'm glad to be able to kind of stay connected through this. So I'm going to share. Oh, I can't share. Can I get permission for that? I wanted to share a couple slides just to kind of get warmed up here. Both. I know that I don't know how familiar people are with Siena models. So actually, let me ask: has anybody estimated a Siena model or a stochastic actor-oriented model? I see a couple of hands. All right, 2.5 hands. Okay. All right, so we will stick on the conceptual level as much as possible. And
are you able to share the screen now? Can
yeah, I'm working. All right, I think I've got that going. Let me start a slideshow. Okay, I think I've got that. Oh, but I lost you all. All right, I'm going to try this a different way. All right, can you all see? You all see slides? Yeah. Oh, okay. Wow. All right. I haven't tried this in a long time. So, okay. So, yeah. So I wanted to talk about first of all, just talk about two-mode networks and make sure we're kind of all on the same page regarding what a two-mode network is before even getting to how to estimate a SOAM, or I'm going to call them Siena models because the software is our Siena, which derives from earlier Windows Siena software, which is really the only way you can estimate these models is within our Siena now. So two-mode network, we've got, you probably talked about this a little bit yesterday, but we've got the defining feature is we have a node set that we have split into two kinds of nodes. And it doesn't matter really what they are. We've got two nodes and we're only considering ties between those two modes. So this might be people and events, and the relation is from people to events. It might be, this is authors and publications in the graph that's shown. Authors are red and publications are the blue diamonds. And we're only looking at the relations. In this case, it's an authorship, author on a manuscript as the connection. There might be all kinds of connections within mode. Authors might be connected in lots of other ways directly. Manuscripts might be connected, appearing in the same journal or other kinds of things, but we're ignoring those when we're talking about a two-mode network. The two-mode network, we are just talking about between mode ties. Now we could bring in those other networks, those one-mode representations, as a multimodal network, and there's more and more methods designed to work with that type of data. But we're going to not really get into that a whole lot right now, because we can just model the two-mode network itself, and that's what I want to focus on primarily. Now, with the two-mode network, there are some constraints that come up that differentiate it from a one-mode network. The most glaring one is that you can't have triangles. Or really any odd-numbered cycle is impossible because every tie connects two different modes. So these really what we think of as in terms of processes like transitivity, structural balance, that's all going to work a little bit differently, if at all. And so that's kind of what I want to a message I want to emphasize is that, things are, with the two-mode network, a lot of things are the same, but there are just some little fundamental differences that really permeate permeate the process of estimating a model. Now for a two-mode Siena model in particular, we're gonna do one more thing, and that is we're gonna take these two node sets. We're gonna call one actors and one we're gonna call non-actors. I call them foci. They might be events, although that can be confusing. They could be, yeah. And the key reason we do that is that with the Siena model, it's kind of the estimation algorithm at the heart of the model is actor-based. So think of an agent-based model, an actor-based model where the nodes are actors and they are making decisions about which ties they are going to have. So in the case of a two-mode network, actors are making decisions about which foci they're going to have a connection to. And within this process, foci are these passive entities. They just they're just there, and actors join them or don't join them, but they have really no say in who joins at all. So they're just there, and all of the action is on the actor side of the model. Okay, so all ties are technically from actors to foci, although you could just kind of ignore that directionality and just keep in mind it's only actors that are joining foci. That also means there's no reciprocity within a Siena two-mode network. That's not true of all two-mode networks. More generally, you might have ties that can be reciprocated in a two-mode network. You could imagine like a heterosexual partnership network where you've got two genders and partnerships can only be between genders. And people reporting on those partnerships, I might report on a partnership and maybe someone reports back or not, or something else about the relationship. So you could have reciprocity in two-mode networks, certain two-mode networks, but not within the Siena model because all the action is just on one side. Okay, so beyond that constraint, that one constraint that of all of the kind of nodes in the network, only one mode can send ties. A two-mode Siena model is, for all practical purposes, the same model as a one-mode Siena model. Kind of everything else works the same. It's just we're only going to let some portion of actors do the tie sending. And so kind of some of the things that happen in Siena models that are important to keep in mind are the set of nodes that are in the network. Those are exogenous. And we kind of know those from the outset of modeling, at least. They're present in our data, and we know exactly who all of the actors are, and we know who all of the events are. And what that means is we don't have actors kind of creating new events as part of a process we can model. That likely happens in real life. I know I study adolescent extracurricular activities a lot, and it happens in schools that a group gets together and it's like, we need to form a club, and they'll find a faculty sponsor and form a club and get official recognition, and we have no way of modeling that with the current models, and so that's something that's kind of missing out a little bit. We're just kind of assuming these clubs exist and students kind of join them through one process or another. We're also assuming that ties are kind of these in states that endure across time to some extent. So you might think of these as memberships, things that kind of go on and maybe they become latent and at some point and fade away, but they're not these discrete event kinds of things. And so we're kind of assuming actors make a choice to keep a tie, and then that or join an event or join an activity, and that just kind of persists for some amount of time. So, so we're not looking at kind of the comparison is relational event data, where you might have actors actually participating in some event, and you've got that recorded over a long many events, and those events have some kind of ordering to them. We're more interested in kind of the structure underneath that, in terms of the pattern of memberships or affiliations that maybe drives that kind of thing. We could talk about how you could turn event data into data that could be conceptualized more as enduring states. That's something we sometimes do with Siena models. We also assume that ties change one at a time. And so, again, thinking back to students and activities, we don't, as a group of friends, we all just don't join the same activity. The model can't handle a group doing the same thing at the same time. What would happen is, with the Siena model, actors are randomly chosen, and then they make choices about an activity they're going to join or stay in, and then another actor is chosen, and they make their choice. And so, if kind of in the natural world there were groups that joined an activity together, within the Siena model that would kind of show up across time, with kind of one person joining and then their friends joining, assuming we have friendship data. If we don't, we're kind of going to miss out on that kind of phenomenon. But we can't, again, the model, kind of the Markov chain that underlies this only allows for one tie to change at a time, and we're assuming that one tie is contingent on the current state of the network, and that decision to change that tie is contingent only on the current state of the network and not other kinds of things. All right, so I'm gonna pause there, and I want to open up to any questions that people have. In particular, I know, again, if you haven't modeled a Siena model, this is even more foreign than a Siena model is, and that can be hard to wrap your head around. So I'm happy to talk about kind of Siena models more generally. The one mode, the old-fashioned one mode version, or two mode versions, or putting them all together. The video put them together a little bit. Talked about that, or really anything else. So are there any questions right now?
There's one in the chat there. Carolyn, you want to go ahead and just ask it out loud?
Yeah. Hi, thank you so much. I thought this was super interesting, and I'm presenting in the design lab tomorrow, and so I think this is also sort of starting to get at some of the questions I was having. So thank you. This has been super interesting. But so I was just interested, you just mentioned, right, that like you would want to be able to incorporate friendship data, but how do you do that if you're only allowed to have ties like between modes rather than within the modes, right? Because friendship data would be like looking at ties like within the actors rather than between modes.
Yeah, right. Great question. So within what we're really going to do is we're going to bring in a second network, and so we've got our two mode network. We're going to model that, and then we've got a one mode network that's the same actors, right? The same nodes on the actor mode of the two mode network. Let's bring that also into the model, and the script talks about how to do that. I can talk about script and data setup. That's kind of a separate. I feel like it's maybe a separate question or a second part of the question. But conceptually, you've got both of these networks, and you're within the model. What you're going to do is specify effects. Okay, these are things we want to model in the two mode network, right? So people join, people join activities with their co-members, right? That's kind of an indirect influence. So if we're in one activity together, we're going to join other activities together. Now that could be driven by friendship, because we know friends join multiple activities together. So what we're going to do there is we can also specify effects that build upon the one mode network. And so, you know, we can specify it. I might have some effects shown in here. This is a co-member influence effect. And I don't know if you've seen these little pictographs or not. This is how a lot of the Siena kind of work is, or effects are described, where, because you're looking at across time. So at time one, you've got two nodes, the circles here, they belong to a certain foci. And then one node belongs to a second foci. And then what we're looking at is, well, across time, does this fourth tie from the other node to the foci appear? Okay, so that's what we're trying to capture with the co-member influence. With the, let's see, where do I have member influence? Okay, so with network influence, we've brought in a second network that's a friendship network. And we have a tie from one node to another in that friendship network. And then one person belongs to an activity, and then the second person, the friend, joins that activity across time. So within the Siena model itself, it's really in some ways quite straightforward to bring in multiple networks, because the actor orientation means that you know, you're simply modeling actor decisions, and we can jump around multiple functions to do that. So there can be a one mode network function, a two mode network function. Oftentimes there's a behavior function where an actor is choosing levels of behavior. We could add on more and more functions to model other things that are changing, that actors are changing as well. So we're really going from one function to two when we're bringing in two networks.
So that was actually one of the questions I had, which was, I mean, it was such a nice presentation to see it on the video, because it was these kinds of examples are so nice to be able to see. But I was curious, like, just intuitively, is there a from the underlying sort of architecture, does the tool treat the two mode network that much, like the actor's choice to join a club, for example, that different from an actor's choice to start smoking, for example?
So does it choose it that different?
I mean, you could treat that intuitively. A two mode network is in many ways another kind of behavior. So in some ways, you can think of it as just a flip side of the behavior function. Yeah.
Good point. So you could imagine. I wish I had a whiteboard here because I could draw this out. You could imagine. So within a behavior function, what we have is an ordered category is our outcome, and you know, let's say smoking, not smoking, right? You're in one state or the other, and your choice is, I'm in my current state. Do I stay here or do I go to the other state? And if you've got more categories, your choice is, do I go up one state, stay the same, or go down one state? So start smoking more, stay the same, or start smoking less. So the two mode is different in the sense that you know, you still have multiple categories. Right. You could join multiple ones.
Yeah, that makes sense, right?
And you can only change one at a time. So you could imagine setting up. Well, you could imagine. You can't have the kind of simultaneously change that you do with a behavior So with behavior, you can stop smoking at level 0 and start smoking at level 1, which is in a sense kind of, you could think of it as 2 changes, but it's really moving.
Well, anyway, it's a great presentation, and I think it's a great tool for people to use. I'm looking forward to using it just to help, because so often you have to layer over, if you're doing it like the ergon kind of model or whatever. You have to do the one mode projection to say that people share a club or something like this, and the ability to just actually deal with the raw bipartite network is really nice here. So.
I think there are a couple other questions.
Allison has a question.
Yeah.
Hi, this is just a clarification. You don't need 2 time periods to use Sienna, right? You can just have 1 time period of data.
Well, so all right. You can model a Sienna model on 1 wave, but it's you typically don't. It's a model of change, so you typically will model change over time. That said, you can model 1 wave if you trick Sienna into thinking you've got data that changes. You can model, you change 1 tie and treat the same network as time 1 and time 2, the model can estimate. There's a Snyders and Steglich paper that does that from 2015. But it's for really weird kind of situations that you would want to do that. Actually, the paper I cite in here, where we developed a lot of this, we do that actually for the friendship network, because we want to hold the friendship network constant and really just look at effects on the 2-mode network. In actual practice, you probably want to, if you have 1 network changing, you'd like to have the other network changing as well if you've got that kind of data. If you only have 1 time point, a 2-mode ergom might be a better choice, but there could be effects that, because these are so new, you might not be able to estimate something that you would want to estimate, and maybe the Sienna approach could be a way to get something like that.
Thank you.
Okay.
Just if we have enough time, I don't want to take us over time, but you've made it really, really clear. The actor orientation is very clear, and you've repeated it in both the lecture and here. But I was trying to think about, so recently I've been reading the stuff about sort of influence and joining cults, and in particular the way that cults are, and because of Jim, and particularly the ways that these foci can be exclusive, right? And so maybe it's a little unfair to the Sienna model that has a particular orientation, but I wanted to know what your interpretation within a Sienna model would be of this, which is once I join a particular foci somewhere in the network, the way that those requirements might pull me away from other. How do I operationalize that in the context of a Sienna movement? It doesn't have to be cults, it could be social movements that have sort of separate perspectives or something like that.
Yeah, that's a good question. My first response would be within a degree kind of effect, out degree kind of constraint, either a hard constraint or something to get at that most people join one group and that's it. That would be something the model would capture. You could imagine variability, where some cults maybe are more, suck up more of your time, whereas others, or maybe it's more organizations, certainly some suck up all your time and some allow you, to have family and other things. You could imagine also operationalizing it, some kind of measure, or maybe you can operationalize that in a measure, is something about the institution, organization, or cult that gets at that, and use that as an alter attribute. And so I could imagine you'd want to probably look through a lot of the different effects related to degree, but a degree effect related to alters attributes, such that alters egos joining a foci with certain attributes maybe don't have as many memberships in others. You spend a lot with, if you get into Sienna, and I see Cassie's here. Hey, Cassie, she can probably second this. You spend a lot of time looking at like these equations and these little pictographs, trying to figure out, is this representing what I think is happening or I want to test in my network? So the Sienna manual, I've said it and I'll keep saying it. You've got to really become fluent with that to become proficient.
All right, thank you so much. And yeah, I would second that. You know, if you're going to dig into these models, you really got to learn the terms. And I think one of the nice things that this presentation in particular so nicely highlighted is the ability to do interactions on the fly, and the way you specify effects really broadens the range of ways you can think about specifying these models. So it really is a pretty impressive set. So.
Yeah.
All right, thank you very much, David. Really appreciate it.
Yeah. If anybody has questions, if they do get to this, feel free to reach out. So.
I think we'll stick with the stochastic actor-oriented model framework here now and switch over to Cassie McMillan. Cassie is an assistant professor at Northwestern, and she has worked widely on a lot of these kinds of stochastic actor-oriented model problems in the past. And she is returning to social networks and health to show a new sort of twist on the way these models work. And so it's really great to see you, Cassie. Thanks for joining us. And I think I need to make you a co-host if you want to share your, I'll do that right now, if we want to share your screen or some such. And I'll turn the floor over to you.
Yeah, sounds good. Hi, everyone. Hi, David. I just caught the end of your talk, but we're going to switch from thinking about two-mode networks back to one-mode networks in SAOMs. And I can share my slides if that would be helpful from the recording. And I'll talk a little bit about them. But I was going to give just like a 5 to 10 minute summary to start and then open it up for questions. But I'm also happy to just chat more too about both time heterogeneity in SAOMs as well as just SAOMs more broadly, if folks have questions. All right, let me do that. So to start, but like when to first think about time heterogeneity in SAOMs, the first thing one needs to recognize is that there's this one assumption that we have in our standard SAOMs that's really, really basic that most people don't even tend to think about it. And this is known as the time homogeneity assumption. So this assumption that what's being assumed here is that any sort of processes that we're thinking about, whether these be network processes, so is a certain characteristic more or less associated with sending or receiving ties, or behavior change processes, we're assuming all of these processes are occurring at a constant rate across all of the waves of our study. So for example, if you have different panels of waves of data on adolescent friendships, as well as on adolescent drinking behavior, and you're interested in looking at something like, are adolescents more likely to be influenced by the drinking behaviors of their friends? When you include an SAOM effect to measure this process, the SAOM effect is going to assume that across all of the different waves in your study, the tendency for adolescents to adopt those same drinking behaviors of their friends is going to happen at the same magnitude and at the same direction. So across all, like if you have data from say 9th grade to 12th grade, the SOM coefficient is assuming that from 9th to 10th grade, 10th to 11th grade, 11th to 12th grade, so on and so on, that all of these processes are going to be completely consistent. So is this a big deal that we're making this assumption? Do we meet this assumption or are we violating it? It really depends on what your data looks like. So for example, if you just have 2 waves of data, not a big deal at all. The SOM coefficient is just taking the average of what's happening between those 2 waves. However, as you have more waves of data, this becomes more and more potentially problematic. And that's especially the case if we have multiple waves of data that were collected across wider ranges of time. So for example, right, if you think back to your own high school experience, the way you thought about your friends and drinking was probably really different in 9th grade than it was in 12th grade. So as a result, there might be some value in thinking about how these processes change between the different waves. And in particular here, I have an example that I kind of worked out of how thinking about and assuming time homogeneity can be really problematic in certain instances. So for example, here, this is from a previous SOM that I estimated, where again, we're looking at friends' average behavior as a measure of influence. And this is specifically for smoking tobacco here. So the SOM coefficient here is positive and significant. What this is telling us is that over the course of this study, the adolescents in the sample were more likely to smoke at similar rates as those individuals who they were friends with across the different panels. This was taken from 6th to 9th grade across 5 different waves of data, specifically from the Prosper study, which y'all might have heard about in some of the earlier lectures that you've seen here. So right, this is how we got this coefficient, but how did we actually get this coefficient? There's kind of 2 different options that we could have had going on. On the one hand, right, perhaps this specific level and direction and significance of the impact of friends smoking on an individual smoking, maybe it was entirely consistent across all the different waves, but alternatively, it could have been very different across the different waves. So right, perhaps in those earlier waves in 6th grade, students were really, really influenced by their friends' smoking behavior. But as students aged, the magnitude of that influence really decreased until they got to later adolescence, and perhaps it ceased to exist entirely. In both of these options, if you want to add these up and take the average, you'll see that, right, the average is the exact same, but these are clearly very different sorts of social processes going on. So right here, things are remaining consistent, but here there's clearly some sort of developmental pattern going on that's shaping young people's experiences with smoking tobacco. So Sienna, it luckily includes some terms to help one piece this apart. And in the lab that R script that I uploaded for y'all, I have some examples of what you can do to include these time heterogeneity ways to measure this time heterogeneity. Also, there's ways you can just check to see if there is heterogeneity in your processes. And it's, again, pretty simple code to do this. It will change the way that you interpret your coefficients a little bit. But that being said, like it's pretty simple after one has an understanding of one mode SOM. So the last thing I do want to briefly touch on before I'll pass it over for questions is about why we should even care about this time heterogeneity. Why is it something that might be of interest to us as health scholars? So the first kind of reason we should care is a bit more substantive. Sometimes you might have research questions where you're really interested in thinking about whether different network processes vary across the waves in your study. So for instance, especially a lot of developmental theories have different arguments that people's experiences with network processes like influence, the popularity associated with a certain type of behavior. There's a lot of different theoretical perspectives about how that might change as individuals age from youth to adolescence to adulthood. By incorporating these time heterogeneous parameters, you're able to actually test whether or not the magnitude of these different processes changes. Additionally, too, if you have like data on a network of people over time, and you're interested in how different network processes develop as people get to know one another better, looking at time heterogeneity coefficients in that kind of environment can also be helpful as well. Another instance where thinking about time heterogeneity from a substantive point of view also can be if you're interested in looking at the impact of some sort of intervention or treatment that occurred in the middle of your study. So for example, imagine you have data on the network and behavior patterns of a group of young people, both before and after they took place in some sort of intervention campaign. Perhaps the goal of the intervention was to teach these young people skills for resisting peer pressure. Perhaps you're interested in if that actually changed the degree of which people are being influenced from their friends. Again, using these time heterogeneous coefficients, you could compare what they looked like or what peer influence looked like before the intervention happened to what it looked like after the intervention happened. And in the later part of my presentation, I have some examples where I take this approach in some of the work that I'm currently working on. And here also too, by thinking about interventions, I'm defining interventions really broadly. So what I'm doing in my work is me and my colleagues are thinking about school transitions, normative school transitions. So this is like the move from a lower level school to a higher level school. Specifically, we're looking at the move from elementary school to middle school. And by using time heterogeneous coefficients, we're able to see whether or not network processes associated with delinquency change both before and after these transitions occur. But so yeah, if you are interested in that, that is in the recording. But I also do want to point out there's two also kind of more technical reasons that we might be interested in thinking about time heterogeneity. And specifically, these are more so thinking about how to better fit your model and get less bias in your estimates. So even if you have a question that where you're not interested in change over time at all, still, if you don't appropriately account for the time heterogeneity of the different SOAM coefficients in your model, it can potentially bias the both significance level and the direction of the coefficients of your other SOAM parameters. So for example, right, if your main effective interest, even if you don't have any reason to suspect that there's any time heterogeneity, that coefficient sign and significance level could still be biased if you are not appropriately accounting for the time heterogeneity of other SOM effects in your model. Also related to that too, sometimes by including time heterogeneity effects or different effects that are really changing a lot across the waves of your study, it can really kind of help improve the fit of your model. So those different diagnostics that are necessary to run to make sure that your SOM is fitting the observed data well, it can improve that fit. And it can also sometimes help lower the kind of risk of degeneracy when estimating these models as well. So I'll go ahead and leave it at that. I'm happy to talk more and talk through the example if that would be helpful, but I'll go ahead and pause in case folks have questions.
Thank you very much. That's awesome. Yeah, so the floor is open for questions or comments. Maybe while we're waiting, I'll seed in one really quickly. Is there a reason not to test for time heterogeneity if you have more than one wave? I mean, is there any reason, like, this seems like a good idea. Why not just do it by default?
Yeah, so I definitely think so. And the code to do it is quite simple. It's not very computationally intensive. You can very quickly just run some tests to see if time heterogeneity is something you should be considering. Then after doing so, like perhaps you might have to respecify your model a little bit, but I think it is good practice to apply these tests, even if time heterogeneity is not of interest to your model or your research question, because it can just help ensure that you are estimating well-fitting models. And also, right, if there is some sort of variety or variation going on there, it can raise new kind of interesting research questions as well.
All right. Cool. Thank you. David, please.
Yeah. Hey, Cassie, great, great stuff here. I'm glad you're pointing this out. I think it's, yeah, something that is, it's important, but it's also kind of, it can be sometimes overwhelming, which might be one reason why you don't see it talked about as much. So I guess my question is more kind of just how would you think about kind of maybe principally, I like your example. You're interested in this peer influence, you know, difference strength across development or time. And let's say that's your research question. How would you go about, you want to test that, but you know, potentially many other things could also be, you know, varying across time and might, you know, and not just on the influence side, but also on the selection side. You know, and maybe you've got 50 effects in your model. Would you kind of, how would you go about thinking, okay, what other kinds of heterogeneity or for what other effects should I really be kind of, you know, thinking about and maybe freeing up to vary across time? Yeah, and is there a principled kind of series of steps one could work through?
Yeah, good question. Because yes, right. If we had all of our effects in our SOMs being time heterogeneous, like then we have hundreds of effects, and it's going to be very hard to get anything to converge with that many effects in it. So what I would recommend doing is first, right, based on kind of your theoretical question and your understanding of the processes that you're thinking about, right, first use that theory and previous empirical guidance to decide, are there specific effects that I really should be focusing on this time heterogeneity in? After doing that, so right, if you're interested in pure influence, how that's changing over time, right, you can definitely account for that. But then after you've kind of figured out those key substantive effects of interest, then what I would recommend doing is running through the kind of diagnostic check that exists in Siena that enables you to see so what these diagnostic checks do, and you can see if you open up the lab and run through it, is they go and take they take your whole model, they look at every single effect you have in there, and then they do tests to see if the direction and strength of those processes, are they significantly different between the waves? And you get a whole report that tells you all of this information. And from that, you can start to see like, oh, wow, transitivity is really changing a lot across the different waves. Maybe I should consider modeling that as a time heterogeneous effect, even though it's not something of interest to me for my research question, but it looks like doing so will help improve the fit of my models. So after looking at that and looking at all that printout, figuring out what makes the most sense is the kind of next step there. But then again, right, if you estimate that model with transitivity modeled as a time heterogeneous effect and you're starting to run into convergence issues, it's not really changing any of the coefficients of your effects of interest, at that point, then probably not necessary to include that, and instead just focus on the effects that are actually converging, or like the specifications that are actually converging.
David had hinted at it, and I think that Cassie laughed at it. But I'm going to just bring it out into the open here. So these models often do have a lot of parameters. I mean, in part because there's lots of you're doing, you know, perhaps 3 different network functions and a behavior function, and everything over time, and there can be, you know, many parameters to look at these models. Is there a sort of generalization of David's first question? Do you have practical advice for like what the minimal set of things are versus, you know, like do you start with the kitchen sink and winnow down? Do you start with just degree and density and move up? Like what's your best practice for getting these, and what can be, like if you just let the sociologist run wild, can be pretty crazy models. So do you have a guidance on just the pragmatic specification issues?
Yeah, no, that's a great question as well, because I think, right, like I heard y'all discussing at the end of David's talk, it can be really overwhelming to like open up the manual and see the hundreds and hundreds of effects that exist. And I was hoping that this like screenshot I took of this table had a bit more parameters in it, but this is like probably like a fifth of the parameters that were included in this model. So they have, typically you'll have 20 to 30 kind of effects in your SOM. And my recommendations for starting out, again, right, figure out which specific effect is modeling the process that you are interested in with regards to your research question. Figuring that out can take some time, going through and figuring out how to make sense of what is in the manual and the different equations and little pictures that they have. Sometimes you'll have to create different interactions or other kind of terms in order to really get at the process you are interested in modeling. But so first, right, that's always the first steps first. The next thing that I would recommend is there's slowly kind of become more and more an agreed upon set of structural parameters that folks include in their SAOMs. And I'm happy to like provide anyone with a list of those, kind of like what I see them as the more agreed upon sort of structural terms that if you don't include, reviewers will be like, why didn't you include that? And this like starts with reciprocity and transitivity, but also includes terms that have to do with the distribution of in degree and out degree in your network. And I would recommend going ahead and including those. Those also are part of the reason that these networks are so computationally intensive and take a long time to run. But by starting and including those, it can really help kind of work through your, help you work through your modeling and specification strategy. Then in addition to that too, thinking about other individual level traits that we know are key controls in a lot of our models as social scientists can be really helpful too. So right here, like these are the behavior change effects. I accounted for how sex and race and different family relations and styles, how all of these different things also shaped one's tobacco use. And this was all just based on previous work and things that we have established and know as social scientists. So making sure that kind of those kind of effects are in there as well.
Awesome.
If I can just chime in, I think it's a great answer. Thank you. So I didn't have to say all that for folks. I would just add, sometimes, especially with a bigger model or bigger network, larger network, it can be tough to really get that first model to converge. And so, thinking about for like kind of that first model where you're first kind of getting familiar with some data, getting it to fit, try to kind of triage what are the major things that are structuring this network. Kind of, with adolescents, it's kind of being in the same classrooms at school, living near each other, being in the same activities, being the same race. These things are kind of, if you want to think about it, they account for the most variance kind of in which ties exist. Kind of putting those in a model, an initial model, along with, like Cassie said, reciprocity, transitivity, these other major things, and then getting that model to converge or get close, and then start building up from there with all of the other things that you think matter. And there's the Siena model has a score test option, which is a way to, because these are computationally intensive, it's a way to kind of list some effects that you're thinking of including, and what the during model estimation, what will happen is those potential effects, their fit is evaluated, and the statistics, you get back statistics saying, that adding this model or adding this effect to the model, this effect really isn't fit by the current model, so adding it should improve fit. So basically, it's a prospective way, without having to estimate all of these effects, to get some sense of whether or not an effect should contribute to model fit.
Yeah, no, I hadn't thought about that kind of diagnostic tool in a while, but that's definitely a useful way to also start, and when just thinking about these models as well. I think, right, especially if you're just starting out, like playing around with very simple models that just include basic effects too, and getting them to work and seeing what your output looks like, seeing what it looks like in your R environment when all of this is running, that can be really helpful too.
Awesome. Allison, please.
Thanks for your talk. Like, I found your presentation, your video super clear. This is more about your R code. You were doing your time test function, and I think like by the end of it, the p-value wasn't significant. So is that telling you like I captured all the heterogeneity once it's fine? Like you kept doing the time test function?
Yes. So let me pull up the R script for me to make sure I'm saying the right information. But yes, so once after the, like when those, so like the output from the time test, it'll be significant if like you aren't properly modeling everything. And once the significance of one of those different like kind of coefficients goes away, then what that is telling you is that it is being appropriately modeled. So that was the conclusion there after we included the different parameters for the time heterogeneity. Things were appropriately accounted for. And in walking through that code too, I showed how, right, sometimes you might only need to include one of the dummies, because right, there might just be one wave where things are really weird, or one wave that you care about for some sort of substantive reason. And so right, by then including that one dummy, looking at the p-value, seeing if there are significant differences that you're not accounting for, that's when that can really come into use. But yeah, good question.
Anyone else? Might take a quick break then. Give Cassie and David both a second thank you for all the help. Maybe we'll take a quick break. Come back at like 10:03, so take 5 minutes or so, and we'll jump into some new work on community detection with Peter.
Yeah, sounds good. Thank you, everyone. And I'm happy to follow up via email if folks have additional questions after you've gotten a chance to look at everything.
Thank you.
All right. Okay.